Hello viewers, in the series of videos related to the chapter Electric Charges and Fields, today we will talk about the concept of electric field and electric field due to a point charge. Now, what do we understand by electric field first of all, right? That means this is something related to the electric charge. Electric field is related to the electric charge. So, suppose we have a charge Q, right? As you can see over here, we have a charge Q, right? Suppose we have a charge Q. Now, this charge Q is said to be, let us call it the charge capital Q as the source charge. That means this is the charge Q which is creating some field, some space around it, within which if we place any other charge, that particular charge will experience a force of interaction. That means a force of attraction or repulsion. Now, the charge which we put in the space around the charge capital Q, that charge is what is called the test charge, and the test charge is usually denoted by small q naught, right? So, over here in the diagram, as you can see, the source charge is capital Q, the source charge is capital Q, and the test charge is denoted by q naught. So, the source charge is producing some space around it, within which if I place the charge q naught, that charge q naught will experience a force of attraction or repulsion depending upon the nature of the charge capital Q, which is the source charge. Because this small q naught which we are talking about, this is called the test charge, and the test charge is considered to be a positive charge. It is considered to be a positive charge according to the convention. It is taken to be a positive charge. So, a charge q naught, small q naught, as you can see over here, the charge small q naught, when placed close to another charge capital Q, which we are showing in the diagram, this q naught experiences a force of attraction or repulsion. Okay. This force is due to interaction of electric fields of two charges Q and q naught. Because capital Q is the source charge, this test charge, which is q naught, which is a very small charge, is considered to be a unit positive charge. But even though it is very small charge, it will also have some field of its own, right? So, the presence of charge Q modifies the space around itself, right? So, the charge Q, it modifies the space around itself, and the presence of charge q naught, the presence of test charge q naught in the space modified by charge capital Q leads to the development of force on q naught. So, this test charge will experience a force of attraction or repulsion depending upon the nature of the source charge, whether the source charge is positive or negative. And therefore, what is electric field? How can we define electric field? This is the definition of electric field. Due to a given charge, electric field due to a given charge is the space around the charge in which the electrostatic force of interaction can be experienced by any other charge. Electrostatic force of interaction. Interaction, as I have told earlier also, it consists of both attraction, it's a word which is used for both attraction or repulsion. It can be experienced by any other charge. So, it is the space around the charge in which the force of interaction can be experienced by any other charge, right? So, this is how do we define electric field. Then the next thing what is there is, how do we measure electric field intensity at a particular point? How do we measure electric field intensity? When I say electric field intensity, this is the term electric field intensity. So what I am talking about is what is the strength of the electric field at a particular point. That is what I am trying to understand. So what is the strength of the field at a particular point? So suppose the source charge is here, Q, capital Q is here, right? It is at the point A. I want to find out what is the field at the point somewhere here, right? So I at the point B. Now this at the point B we will place a test charge, that is your Q naught, right? So whatever is the force experienced by the test charge, that is the test charge is a unit positive charge, force experienced by a test charge placed at that particular point will give us the electric field intensity at any point. So the source charge is at the point A. If I want to find out what is the electric field intensity at the point B, then at the point B we have to place a test charge, which is a unit positive charge, and whatever is the force experienced by the unit positive charge placed at the point B is termed as electric field intensity at the point B. It is termed as electric field intensity at the point B, and therefore it is written as E, which is nothing but E is equal to F vector upon Q naught. E's vector is equal to F vector upon Q naught, because the direction of field will be in the same direction as that of the force. Now the force and the field direction will be same. So suppose we have a positive charge. Q is a positive charge, right? Q is a positive charge. So the direction of field at the point B will be in this particular direction, that is away. It will be directed away from the source charge, right? Now if the charge capital Q is negative charge, then the field at the point B will be directed towards the source charge, because in that case the field direction will be towards the source charge because it is a negative charge. Okay, have you understood? Because it is a negative charge and therefore it will be directed towards, because it will be a force of attraction. This is negative, but our test charge is nothing but a unit positive charge according to convention. Therefore there will be a force of attraction. When I say the source charge is positive, the test charge is also Q naught, which is also positive. So there will be a force of repulsion, and that is why it will be in this particular direction. It will be directed away from the source charge, whereas when the source charge is negative, the field direction will be towards the source charge. Have you understood this? And what will be the unit of electric field intensity? Because we know SI unit of electric field intensity, we know that force is measured in Newton and the charge is measured in Coulomb. So the unit of electric field intensity will be Newton per Coulomb, right? Dimensions of electric field intensity I will show you in my next slide. Just now I'll work it out and show it to you how we get these particular dimensions. As I told you, the direction of E vector is the same as that of F vector. E vector is along the direction in which Q naught would move if free to do so, right? Q naught will also have its own field and it may modify the field of Q. As I told you, Q naught, though it is a unit positive charge, it is very small, but it may also modify the field of the source charge. Therefore, in order to understand and in order to define the electric field intensity at a point very precisely, what we say is that we write it down, this particular expression, as E vector is equal to limit of Q naught tending to 0. Mind you, this is Q naught tending to 0, but it is not 0, which I am trying to tell you that it is very small. F vector upon Q naught. That's how we write it down. So why do we write it down as Q naught tending to 0? Because we are trying to say that Q naught is not actually modifying the field of the source charge. The test charge is not actually trying to modify the field of the source charge. That is why we are saying that it is very, very, very small, and that is why we write it down in this particular format. Okay, so now I'll just show you how do we get the dimensions of electric field intensity. So here you can see over here that E is equal to F upon Q naught, right? F is the force and Q is the charge. Now earlier I have already told you force as it is, you know, it is nothing but mLT minus 2 upon what is Q? Charge. And charge can be written as, it can be written as A into T. It can be written as A into T. So what do we get the dimensions of electric field as? Dimensions of electric field will be M, L, T, minus 2 is here, and this T which is in the denominator will also go to the numerator. It will also become minus 1 more. So it will be minus 3 into A minus 1, right? So this is M1, L1, T minus 3, A minus 1. So we have got the dimensions of electric field. Okay, as you can see, M1, L1, T minus 3, A minus 1, you have got the dimensions of electric field. Have you understood? Okay, so we'll move forward, and now we talk about what is electric field intensity due to a point charge, right? So now we are considering, as we had considered in the Coulomb's law statement also, we considered point charge. That means discrete charges. Point charge, very, very small charge whose dimensions are very small. It's a small charge and dimensions are very small as compared to the distances over which its effect can be felt. So it's a point charge that we are considering. So at the point A, we have considered a point charge capital Q, and we are trying to find out the field at the point P, which is at a distance r from the source charge capital Q. So when we are trying to find out the field at the point P due to the source charge at the point A, we have to consider a test charge Q naught being placed at the point P, right? So here AP, as you can see, is equal to R, AP is equal to R, and a small test charge Q naught is placed at the point P, right? According to Coulomb's law, we know the expression, we can write down the expression. According to Coulomb's law, we know F is equal to 1 upon 4 pi epsilon naught, which is nothing but we are talking about in vacuum. Okay, so 1 upon 4 pi epsilon naught is electrostatic force constant. Capital Q, which is the source charge, into test charge, which is Q naught upon R square. Right? If I want to write down this expression in the vector form, then what can I do? I can put a vector sign over here and I can write it down as r cap, where r cap is a unit vector, directed from Q, capital Q, towards Q naught, right? And what will be the direction of this force? It will be directed away from the source charge, because source charge is also, we are considering it to be positive, and the test charge is a positive charge Q naught. So this is directed away from the Q towards, directed away from the source charge, right? So the force will be in this particular direction. Now therefore what will be the field? The field will be E vector is nothing but F vector upon Q naught according to the definition which we have done just now, and therefore your E vector will be equal to nothing but F vector is this Q naught upon R square into K, which is 1 upon 4 pi epsilon naught into R cap. So Q naught and Q naught gets cancelled. You are left with 1 upon 4 pi epsilon naught capital Q upon R square into R cap, right? Capital Q upon R square into R cap. And what will be the direction of E vector? It will be the same as the direction of the force vector, right? Direction of E vector, that is electric field vector, will be the same as the direction of force vector, that is capital F. So E will also be in the same direction as F, right? That means away from the source charge. Okay. So now direction of electric field vector is the same as the direction of force. I have told you just now. E vector due to a given charge depends only on the distance r, because we have written down the expression E vector is equal to 1 upon 4 pi epsilon naught capital Q upon r square into r cap, right? So if I want to understand capital Q, it's a charge, and 1 upon 4 pi epsilon naught is also nothing but a constant. So what is it depending upon? E is depending upon 1 upon r square. E is depending upon 1 upon r square, right? That is, it is depending upon the distance r. As the distance r goes on increasing, the magnitude of field will go on decreasing, right? Because as r goes on increasing, magnitude of field will go on decreasing, because E is inversely proportional to r square, right? And if you have equal distances from the source charge, then magnitude of E will remain same. So suppose we have a point charge at the center of a sphere. If you have a point charge at the center of the sphere, this is a sphere, and if you have a point charge at the center of the sphere, then because on the surface of the sphere, the distance of the points on the surface of the sphere will all be same from the point charge which is at the center O. Therefore, the electric field at every point on this particular surface of the sphere will be same, right? The electric field at every point on the surface of the sphere is same. That is why it is said that electric field due to a single charge is spherically symmetric. It is said that electric field due to a single charge is spherically symmetric. Okay. We'll continue further and talk about now electric field intensity due to a group of charges. Just as we had talked about what is the force on a charge due to a number of charges, right? Similar, and we had used Coulomb's law and the principle of superposition there. Similarly, we over here we find out what is the field intensity due to a group of charges, right? Due to a group of charges. Again, it is given by the vector sum of the electric field intensities due to given charges at a given point. So suppose you have number of charges Q1, Q2, Q3, Q4, etc. and there is a test charge Q0 over here, right? There is a test charge Q0 which is at this particular point. Now the distances of the Q0 from Q1, let us say, is R1 vector. Distance of Q0 from Q2 is, let's say, R2 vector. Similarly, R3 vector is the distance of the test charge Q0 from Q3, and also R4 vector, and so on. So now here, because Q1, Q2, Q3, Q4, we have all considered that to be positive charges. So the fields will be all directed away from these charges. So this is the direction of E1 vector, E2 vector, E3 vector, and E4 vector. And due to a point charge, we have already written down the field just now. That is, E vector is equal to 1 upon 4 pi epsilon naught Q upon R square R cap. Now similarly, if you want to find out what is the field at a point, right, due to a group of charges, and the field at a point we are trying to find out is P, let's say, we have placed a test charge Q0 there, right, and therefore the field at the point P due to number of charges will be given by E1 vector, which is the field due to the charge Q1 at the point P, E2 vector, which is the field at the point P due to the charge Q2, and so on. And this is, let's say, the nth charge. Okay, so similarly we can write all these fields. So E1 will be nothing but E1 will be equal to 1 upon 4 pi epsilon naught q1 upon r1 square, right? q1 upon r1 square into r1 cap if I want to write it down in the vector form. Similarly, I write it down for E2 and E3 and En, and hence we write it down as E vector is equal to 1 upon 4 pi epsilon naught will be common. We take out common. Summation of I is equal to 1 to n, right? Qi upon Ri square into Ri cap. So when I substitute I as 1, I get this expression. When I substitute I is equal to 2, I get the second expression, that is E2 vector will be equal to 1 upon 4 pi epsilon naught Q2 upon R2 square into R2 cap, where R1 cap, R2 caps are nothing but the unit vector directed from Q1 towards Q0, right? So this is what have we done. We have used the principle of superposition and the definition of electric field intensity due to a point charge at a particular point, and found out what is the field due to a group of charges. Now all these charges are also discrete charges, q1, q2, q3, q4, they are all discrete charges. Okay, so we have found out this. Thank you. If you want to see more such videos, hit the subscribe button and like and share the video. Thank you.